see about the PN junction diode. So we know PN junction diode is formed by combining a p-type material with an n-type material. We know a p-type material is obtained by adding a trivalent impurity to an intrinsic semiconductor where the majority carriers are holes and the minority carriers are the free electrons. Similarly, an n-type material can be formed by adding a pentavalent impurity to a pure intrinsic semiconductor crystal. So here we know in n-type semiconductor the majority carriers are the electrons and the minority carriers are the holes. Now coming to the formation of a p-n junction diode, we have different methods for the formation of p-n junction diode: grown junction type, the fused junction type, diffused junction type. So in the grown junction type, an extrinsic semiconductor is grown from the melt, and at the middle of the process impurities of the opposite kind are added to the melt so that the opposite type of crystal grows further. And in the fused junction type, a p-type and n-type material are kept in contact and they are fused together by heating it to a very high temperature. Then in the diffused junction type, we have basically two methods in this one: the solid diffusion method and the gas diffusion method. In the solid diffusion method, a p-type impurity is painted on an n-type wafer and it is heated. Then these impurities atoms are then diffused into the n-type material and they will be forming a p-n junction. And in gas diffusion method, a wafer of n-type semiconductor, it is heated to around 1000 degrees centigrade in a gaseous atmosphere of high concentration of trivalent impurity. So these are the different methods for formation of p-n junction diode. Now when a p-n junction diode is formed, that is when a p-type material and n-type material are combined, then the interface between those two materials will be called as the p-n junction. So it is a two electrode device. One is the anode, the other one is the cathode. Diode in the sense two electrodes. One is the anode, the other one is called as the cathode. Now this is a symbol for a p-n junction diode. So the vertical line is going to indicate that it is a cathode and the other side is going to indicate that it is the anode. And this is how a real component of p-n junction diode looks like. On one end of the diode we are going to have a strip which is going to mark that side is the cathode. The way we apply the external voltage for this one, for a p-n junction diode, is called as the biasing. So basically we are going to have three biasing conditions. One is the zero biasing condition where no external voltage is applied to the p-n junction diode. Then we have the forward bias, then the reverse bias conditions for the p-n junction diode. We'll see one by one. First, the zero biased condition. In this zero biased condition, there is no external voltage applied to the p-n junction diode. As soon as a p-type material is combined with an n-type material, a depletion region is formed. Now we can see here there is an p-type region here, there is an n-type region, and this dotted line is going to indicate the p-n junction. So because of the concentration difference between the n region and the p region, the electrons will be flowing from the n region towards the p region. Similarly, there is a flow of holes from the p region to the n region, which is called as the diffusion. So because of this diffusion, the holes are moving into this n region. It is going to leave behind negative ions on this side. Similarly, the electrons, when they are leaving the n region, they leave behind positive ions. So on either side of the junction, we have positive ions, that is towards the n region, and on the other side of the junction, we are going to have the negative ions getting accumulated towards the p region. So this accumulation of charges in this region will be giving rise to a potential difference. So here we have the positive potential, and here on the other side we'll be having the negative potential. So this is acting as a barrier for the further movement of the electrons and holes. So this barrier is called as the potential barrier, and this region we call it as the depletion region, as this region is depleted of the mobile charge carriers. We can see in this region we don't find electrons and holes in this region, which are called as the mobile charge carriers. These are the immobile ions. What we have in this depletion region are the immobile ions. So this is the potential difference across the junction. Now what do you mean by forward bias? Forward bias means a p-type semiconductor is connected to the positive terminal of the battery and n-type of the semiconductor is connected to the negative terminal of the battery. Now since we are connecting the p-type to the positive terminal of the battery and n-type we are connecting to the negative terminal of the battery, the holes in the p-type, they will be repelled by the positive terminal and they move towards the junction. Similarly, the electrons in the n-type, they get repelled because of the negative terminal and they will be moving towards the junction. Thereby the depletion region will be getting reduced. So you can see here the depletion region is becoming narrower. You can see here there is a wider depletion region, but because of this forward bias the depletion region is becoming narrower here. Now we can see here the VI characteristics of the PN junction diode in the forward bias. Now this is the applied voltage, forward voltage. As we are increasing the forward voltage, initially the current will be zero. That is, when forward voltage is equal to zero, the forward current will be equal to zero because of the existence of the potential barrier here. Now as the applied voltage is increasing, is exceeding that barrier potential, then the current starts increasing rapidly. Like so, this particular voltage where it is going to exceed this barrier potential is called as the E voltage or the cut-in voltage, or it is also called as the threshold voltage. Now next, the reverse bias condition. Now in this reverse bias condition, the p-type is connected to the negative terminal of the battery and the n-type is connected to the positive terminal of the battery. So this is called as a reverse bias. In this reverse bias, the holes in the p-type, they get attracted towards the negative terminal of the battery and they move in this direction. You can see the hole movement shown with this arrow, and the electrons, since they are connected to the positive terminal of the battery, they move in the opposite direction. Since the holes and the electrons are moving away from the junction, the width of the depletion region will be increased. So you can see here there is a wider depletion region in case of the reverse bias condition. Because of the wider depletion region, there will be theoretically no current flowing in this reverse bias condition. Now we can see here the VI characteristics of the PN junction diode. As we are increasing the reverse voltage, there is a small current we are seeing here. Current is because of the minority carriers, because for the minority carriers the applied voltage is like the forward bias, which is called as a reverse saturation current. So as we are increasing the voltage, at a particular voltage, the barrier will be broken down completely, and from there the current starts increasing rapidly. So this is the breakdown voltage. These are the VI characteristics of the PN junction diode as I've explained just now. Forward voltage taken along the x-axis here and the forward current, and we are representing in the same diagram the reverse voltage and the reverse current here. Now we can see the energy level diagrams here. That is, this is the energy level diagram in the forward bias condition, and this is the energy level diagram in the reverse bias condition. Now you can see here this is the depletion region. So the potential is given by VB, which is the barrier potential. Now applied voltage is given by V. Since it is in the forward bias, the net voltage here will be equal to VB minus V, because the barrier voltage, it is in this direction, that is from N to P, while the applied voltage is in the opposite direction. Since these two voltages are in the opposite directions, so we'll be having the barrier potential decreasing. So the barrier potential now that is given by VB minus V. Now we can see here the reverse bias condition, the energy level diagram, as both of them are in the same direction, the potential is given by VB plus V. So here you can see the barrier potential is increasing. There will be no flow of electrons and holes from one region to the other region. Actually, no current flows.